You probably assume that when a system adopts a tool, it's a pretty straightforward exchange. There's a problem, you add a tool, and your capability goes up. But that assumption misses a critical, hidden part of the bargain. The tool doesn't just change the work. The system itself changes around the tool. And in doing so, it often ends up trading away its future flexibility for today's efficiency.
So, let's start at the beginning. A system correctly identifies a problem. It brings in a tool as the logical solution. This is a perfectly rational move, designed to make the system more effective.
Here's the catch, though. This relationship is never one way. The very moment that tool is put in place, the system itself starts to change. The solution doesn't just fix the initial problem, it starts reshaping the very system that had the problem to begin with.
And this brings us to a fundamental mismatch. The common belief is that tools give us more freedom, more options. But the underlying mechanism is often the opposite. They kickstart a process of path dependence, where the decisions you make today start to narrow the possibilities of what you can do tomorrow.
Okay, to make this concrete, let's imagine a team working in a warehouse. To get more efficient, they build their own custom carts. These things are perfect, sized exactly for the boxes they move and the narrow aisles they have. And right away, their speed and efficiency shoot up.
So, to really understand how this happens, we need to look at what's called the social-technical bond. This is the deep connection that forms between people and their tools. The solution, you see, doesn't just sit in the system. It becomes a part of its very structure, fusing human habits with technical hardware.
The core idea here is the socio-technical system. And really, it's a simple concept. It just means that the social parts, the people, their skills, their daily routines, and the technical parts, the tools, the software, the procedures, they aren't separate things. They're completely intertwined. And they interact through a process called joint optimization. This is where the social and the technical elements sort of co-evolve. People don't just use the tool, they change how they work to fit the tool. And in turn, the tool gets refined to better fit that new way of working. You can see how this creates a really powerful feedback loop. A new tool shows up, people then adapt their processes to get the most out of it, and then the tool itself gets tweaked to be even better for these new, specialized processes. Each step just reinforces the last one.
So, back in our warehouse, this process unfolds just as you'd expect. The team gets incredibly good at using these specific cards. New warehouse layouts are designed with aisles measured precisely for these cards, and nothing else. The entire system, both the people and the place, optimizes around this one single solution.
All of this optimization, well, it creates a path of least resistance. Sticking with the current tool becomes the easiest, most logical thing to do. But this efficiency comes with a hidden price tag, the enormous cost of ever trying to change course.
This is path dependence in a nutshell. A system's future options become boxed in by decisions made in the past. It doesn't even matter if a much better tool comes along later. The system is now physically and socially structured in a way that makes adopting it incredibly difficult.
The biggest barrier here are the switching costs. And we're not just talking about money. We're talking about the total, all-encompassing effort it takes to move away from a deeply embedded tool or process. It's the price you pay to get off the path you're on. Think about what these costs actually are. You have to retrain people who have become absolute experts in the old way of doing things. You have to completely re-engineer workflows built around that old tool. And you have to replace all the other little components that were integrated with it. But even these costs, as high as they are, don't tell the whole story. They aren't the only barrier. The very nature of the connections being formed inside the system, well, that creates another, even deeper layer of rigidity.
And this brings us to the idea of hidden interdependencies. It's really important to understand the difference between a system where parts are merely connected versus one where they have become structurally dependent on each other.
A connectivity link is optional. Think of it this way. Node A can work with Node B, but it doesn't have to. A dependency link, on the other hand, is not optional. For Node A to function at all, it absolutely requires Node B. The link is no longer a choice, it's a structural necessity.
The consequence of this is direct and unforgiving. If you remove that support node, the dependent node just stops working. It's not degraded, it's disabled. Failure in one part is transmitted instantly across that dependency link.
Let's look at our warehouse again. Those highly optimized carts now use a unique wheel that can only be bought from a single supplier. The entire workflow doesn't just use this wheel anymore. The system now structurally depends on its availability to even function.
And right here, the system hits an inversion point. The very solution that drove its success now becomes the main thing holding it back. Its past optimization has hardened into present-day rigidity.
Now imagine an external pressure shows up. A new, more efficient industry standard for box sizes is introduced, and pretty soon everyone else is using it. To stay relevant, the system has to adapt.
But it can't. The custom carts are now the wrong size for the new boxes. The aisles, which were perfectly optimized for the old carts, are now too narrow. The team's highly specialized skills are, overnight, obsolete. The entire system is in a state of lock-in, trapped by its own past success.
This state of lock-in reveals the system's hidden fragility. A structure that looked efficient, that looked robust, was actually becoming incredibly brittle. And this brittleness didn't come from a mistake. It emerged from the very logic of optimization itself. And this is the absolute key takeaway. The system failure isn't a dramatic event, like a part breaking. The failure is a state, the inability to adapt. The system has become so perfectly tuned for one specific environment that it's lost the capacity to survive in any other.
Ultimately, this all points to a fundamental trade-off. A system can choose to optimize for efficiency, perfecting its performance for the world as it is right now. Or it can optimize for adaptability, preparing itself for a future it cannot predict. The logic that drives the system toward one often comes at the direct expense of the other.